Hello everyone, I'm honored to be here to introduce my work, Semantics-Reconstructing hashing for cross-modal retrieval. My name is Peng-Fei Zhang from the University of Queensland. Now let's see the main contents. Nearest neighbor search is a kind of retrieval technique. Give a query point Q, it returns the points closest to Q in the database. This technique plays a fundamental role in information retrieval, data mining, and computer vision. However, with the development of the information society recently, the amount of data has become larger and larger, which leads to the expensive storage cost and time-consuming query speed. Well, in this case, nearest neighbor retrieval for large-scale databases become challenging. So, to tackle this, hashing methods are proposed. It aims to map real-valued and high-dimension features into compact binary codes with the original relationships preserved. With a binary representation, the storage cost for data points can be dramatically reduced. Furthermore, hashing-based nearest neighbor search is able to achieve a constant or sublinear time complexity. Well, due to these attractive properties, hashing has become a promising choice for effective nearest neighbor search in large-scale databases. Most pioneer hashing methods are employed to deal with unimodal searching tasks. However, in real world, multimedia data more often comes with multiple modalities, such as texts, images, and videos. Well, this means sometimes people may need to retrieve data across different modalities. For example, searching targeted images with a certain text sentence. Therefore, cross-modal hashing recently has been broadly studied, including unsupervised method, semi-supervised method, and supervised method. Well, despite the great success achieved, there are still some problems need to be first considered in existing supervised cross-modal hashing methods. The first is how to effectively make good use of semantic information. And as data from different modalities resides in different feature spaces, it's essential to bridge the modality gap. The third is how to solve the discrete optimization problem. And lastly, we need to carefully consider how to make the algorithm scalable to large-scale datasets. While considering these issues, we propose a novel supervised cross-modal hashing method. For simplicity, we restrict our discussion on build model cases. However, it can be easily extended to deal with the conditions of more modalities. Well, now assume we have a dataset X which consists of image and text pairs. Y is the ground truth label matrix. Give the dataset's data. The purpose of our method is to learn the unified binary codes B and the hashing project functions. In addition, F represents the immediate representation, which we'll elaborate later. Well, many methods conventionally learn presentation for data under a classification framework with the semantic labels as the guidance. However, these methods do not consider to guarantee the learned presentation get enough semantic information from labels. Considering this, we introduce the rightmost objective function. We assume that if we can learn presentation that preserve the semantic information, then we can induce semantic information with the learned presentation through a simple projection. And to gain efficient binary project functions for multimodal data, which can preserve similarity relationships across various modalities, we project data from different feature spaces into a common subspace and define the following objective function. And for binary embedding learning, we map semantic presentation F with a rotation matrix into binary codes. In such a way, the quantization error can be further reduced and we can directly learn binary codes without any relaxation. Integrating the above objectives together, we can get the final objective function. By reconstructing the semantic representation from labels, The first two terms can make the semantic representation contain the substantial semantic information of labels, and by building the projection from semantic representation to hash codes with a certain, we can directly obtain the hash codes without any relaxation, so the quantization errors can be reduced. The first one is utilized to generate modality-specific hash functions. More specifically, it maps the samples from different data sources into a common space and preserves similarity between them. The last is a regularizer. Well, as for the optimization problem, we design an interactive scheme to solve the discrete optimization problem of the above function. We update one variable while other variables fixed. Firstly, for representation f, we simplify the objective by expanding each item and then removing irrelevant items. Then we can get the solution through setting the derivation of the simplified equation with respect f equal to 0. As for the matrix U, V, and W is very similar as that of F, so we don't discuss it again. As for the rotation matrix we first compute the singular value decomposition of the objective function and then we can get the solution. As for B, we can directly learn it through a simple sine function. So in this way, we can directly solve the optimization problem. That's the overlearning scheme. Well, the learning algorithm interactively optimizes each variable until it converges. And to verify the effectiveness of the proposed method, we conduct extensive experiments on three widely used databases: Wiki, MyFlickr, and Nasswide. We compare our method with 9 state-of-the-art shallow methods, including unsupervised methods and supervised methods. We choose mean average precision, precision recall curves, and top-end precision curves as performance metrics to evaluate the proposed method and all the competitors. Now we report the MVP results and all of the compare method on 3 datasets. From the results, we can see that the proposed method outperforms all baselines in all cases. Secondly, generally speaking, with equivalence increasing, the performance of all methods keep increasing, which means that utilizing longer hash codes can contain more semantic information. Well, we also plot the top-end precision curves. From these curves, we can have the same conclusion that our method has the best overall performance. In addition, we can also observe that most of the supervised methods outperform the unsupervised ones, reflecting the importance of supervised information in the learning of binary codes. And from the precision recall curves, the proposed method consistently performs better than other competitors. All these results demonstrate the superiority of our method. Well, to sum up, in this paper, we propose a scalable supervised hashing method for cross-modal retrieval. It learns efficient and effective hash code semantically consistent with semantic information by reconstructing the semantic representation with labels. Moreover, with the semantic presentation, it contrasts the correlations with the original features, labels, and the bound codes for the entire dataset. Furthermore, it simultaneously learns the hash codes and hash functions without any relaxation, reduces the quantization errors, and makes the optimization easy to be solved. Well, that's what I want to say for this topic. Thanks for your time.